So this is live session 4. Today I'm taking the live session for some doubts and some like fabrication process. I'll explain in this live session. Let's go through the uh, slides one by one. Okay. So for the fabrication, there will be different types of materials can be used. Here I'm showing this silicon, glass, thermosets, hydrogel, thermoplastics, paper, elastomer. And for research purpose, this top right corner materials can be useful. But for the commercial one, it should be like cheaper and viable. So the down left side materials are very useful for the device fabrication and commercial use. So we have to think about the different methodologies. Here I mentioned how how many types of fabrication techniques are possible for the micro and nanofluidic devices. So first one is a casting. So in that two parts of resin is mixed and poured into a mold. Then stamping used for the fabrication of plastic microfluidic parts. Then rolling and laminating types of high through output stamping. Then micro machining, where this rotor tools or lasers can be used. So, and another one is injection molding, where the this is the first choice for the large fabrication process of microfluidics. Then another one is etching. So there it can be a highly reactive chemical can be used for the wet etching, and for dry etching it can be a reactive ion etching method where the plasma and gas can be used. Then additive manufacturing also possible where this 3D printing also can be done for the microfluidic fabrication. So here I have shown this the left side image, the mold fabrication where this photoresist has been spin coated on the substrate, and after that is this is shows that the temperature for the soft baking is gradually increasing and then gradually decreasing to the room temperature. Then this has been exposed with a UV light, and after the lift of the after the exposure, this is how it looked like. Then after that lift off, this kind of patterns forms on the um, substrate. The pink um color is showing it is resist cured resist. And after this, baking and rinsing can has to be done. This in the side has been shown that how the microfluidic channels are uh, designed. So first, this PDMS solution will be casted on the this pattern. Then it will be lifted using the peeling off. Then after that peeling off, this after plasma treatment and pressure bonding, this how the final product look like, and it can be used for the application shown in the figure C. Then uh, there are different types of fabrication technologies possible: micro cutting, ultrasonic machine, um, ultrasonic machining, then EDM, ECM, laser ablation, focused ion beam, E-beam, X-ray, Liga technique, MEMS process, and micro SM. So they have different uh, achievable roughness. Minimum features can be achieved. and how much tolerance is possible, and aspect ratio also has been mentioned here. And the fabrication of the micro slash nanofluidics has been shown here, where the figure A shows that a different uh, like wave displacement chamber, interruption gaps, wall seat, micro chamber, fluidic channel, microcontrol uh, channel, and the figure B shows that how it can be used. The valves can be used um, during the fabrication. So here this three layer techniques, three layer techniques has been used. The first one is the control layer, second one is the PDMS membrane, and third one is the fluidic channel, fluidic layer. So in this state, this is the closed valve state where there is nothing is flowing to the through the microfluidic channel. But when the vacuum is created, so the flow it it allows to the flow to one direction to another. It is called the open valve channel. And here is one this inlet control layer, inlet of vacuum outlet, PDMS membrane, fluidic layer, and concentration gradient generators are possible here. Then array of cell culture micromembranes. This kind of thing is how possible. And here you see this. This is a different type of fabricated device where almost five layers are there. So what is happening here? This dye, yellow dye with water and blue dye with water, are propagated through this fluidic channel. So because of this three-dimensional flow of fluid, it can interfere in a different way and it can generate the different gradient solution in the device. So this is a five-layer split and recombined micromixture. This is the uh, 19 layer 19 layer London underground map against two UK 50 pence coin has been shown for the size of the device. Then the fabrication of the microfluidic and nanofluidic devices has been shown here. In that figure A shows the hot embossing technique, loading and alignment. So the mold has could be aligned with a polymer where after heating and pressure, using the contact, it can be molded and it can generate the fluidic channels. So it depends on the three things like temperature and load and demolding also. How much possibilities. Then microinjection molding also can be possible where this mold and the like it is like a mold and when this flows form the melted polymer will be uh, pressurized inside, then it will be demold or injection possible. Fabrication of micro slash nano fluidic devices. So here what is happening is this is the rear device, this is the front device, and where it is having three layers, the electrode layer, adhesive layers, and microfluidic body. And the fabrication of the micro slash nanofluidic devices has been done using the photoresist technique, or you can say that semi-adhesive roll-to-roll process, where what is happening first is the film substrate with sheet metal has been taken, then lamination has been done by the dry film photoresist, and after the UV exposure, development has been done of the micro has been, can be done. Then using the electroplating technique, the metal can be deposited on the metal surface. The uh, open area and photoresist removal has been used for the removal of this uh, lamination. sheet metal layers. Then this is the another technique how it has been done. So first photolithography, then development, then copper etching, then stripping of the photoresist, then chromium etching, then laser dicing is possible in the industrial level. And also it can be done with a viable low-cost microfluidic. It can be done via the fabrication of the low-cost uh, technique, where this photo paper and PCB plates, because as a photo paper has been kept, and with that, this kind of patterns uh, fabricated that can be uh, look like this after the patterning. And this is the feature side version of the photo paper and the toner layer on photo paper, and this is toner layer on PCB plate and a master after development. So this is the device, this is the pattern, molding pattern, and this is the PDMS after curing on this pattern. So this is the actual device now. It look like this. So this is a very low cost microfluidic channel. So we have discussed the techniques how we can fabricate, but there are also different materials possible with the different applications. Here I'm showing the uh, different materials, what can be used for the microfluidic device fabrication. Silicon microfluidic chips, glass microfluidic chips, PDMS, thermostat, polystyrene, polycarbonate, polymethyl methacrylate, Teflon, and ceramic, paper, aerosols, cyclic olefin copolymer, COC. And here we'll stop the discussion about the microfluidic channel. Now we'll go for the question and answer sessions where we'll discuss the problems and we'll try to fix all the problems whatever have it's mentioned here. The problem of number one is what is the characteristic length of scale of nanofluidics. So here it is mentioned the first option is 1 to 1000 nanometers, B is 1 to 100 nanometers, C is 10 to 100 nanometer, D is 100 to 1000 nanometers. So uh, the answer would be for this is uh, I can say uh, the dimension we can mention flow dimension I can say. So the dimension that controls fluid behavior in nanofluidic devices range from the 1 to 100 nanometer, and typically the dimension of the fluidic channel. So I can say that the option number B is the right answer for this. So that one here is the right answer. And the channel diameter varies in that term, uh, like 1 to 100 micrometer. Sorry, nanometer. Now we'll go for the next problem. So the next problem is the acceleration vector in a fluid is given. A is equal to 4 t to the power tq plus 3 e square plus 2t. And the unit has mentioned in the micrometer per second square. What is the velocity of it at t is equal to 3 seconds? So, so what will be the answer for this? So we have to find out. So for that, we can go for the acceleration is the we can do the integration of the acceleration. So we'll get the velocity equation. So if we'll do 0 to t for acceleration, then it is a velocity. So 4 0 to t plus so 4 0 to 2 plus t plus 2 0 to theta. How what will do? Here you can see this the integration of this will be velocity of 4 will be of e to the power 4 divided by um, divided by 4 plus t cube 3 divided by 3 2 t square divided by 2. So everything cancel out this 4 3 3 2 everything. Now we will be having formula in cube P4 cube P4. And the answer we can calculate using the putting the T is equal to uh, 3 to the power 4, 3 to the power 3, 3 to the power 2. It will be almost 1 time. Right circular equation in this. Now we go for the another problem. So the question number three is saying that a flat plate scometer as shown in the figure. So, okay, I forgot to mention the figure. So after discussion, after doing this, I'll try to after reading this, I'll try to make a figure. Is to be designed to measure viscosity of a fluid. The height of the channel is 10 micrometer. Its width and length is 10, 5 to 10 centimeter. Magnitude of shear stress on upper plate by fluid is given by tau is equal to mu u upon h. And the upper plate of the viscometer is moving from with constant speed of 1 meter per second. The force applied to maintain this speed is 0.1 N. So let's do this. Okay, the problem can be solved using this formula where I mentioned here the figure how it is looking at. So this is our like viscometer. Here the width is around 5 and length is around 10 centimeter. And the height is around uh, let's say 10 micrometer. Force is around 0.1 Newton. And then the speed, the viscometer speed is around, upper speed is around 1 meter per second. Now we'll calculate the things, how it will look like. Uh, First we'll go for the force. So force is mentioned as is equal to 0.1 Newton, and weight is mentioned as 10 micrometers, so it will be 10 to the power 5 minus 5 meter. Then area is mentioned as a 50 centimeters square. So here it should be square of our dimension. So 50 centimeters square we have to convert into the meter from 10 to the power minus 2 meter. Now the tau we already has mentioned in the figure that tau is equal to mu u by h. If we calculate the mu if you have um, tau we can calculate using the force upon the area. So the force upon the area is around 10 to the power uh, like 20 meter 20. Then if we keep all these things, then we can calculate the mu. Mu is equal to tau h by u or mu is equal to 20 into 10 to the power minus 5 meter. So this is our answer for that. So So it will be around 10 to the power minus sorry 20. So this should be around to 2 into 10 to the power minus 4. So this is the answer is D. So correct answer is D. Then we'll go to another problem where we can see that which among the following is a naturally made microfluidic micro channel present within the human body. So the correct answer is capillary here. It is presence in the middle of the artery and vein. These are the capillaries. And question number 5, which among the following explanation applies to survival of cancer cell in high stress condition inside micro uh, capillaries by sand. So, so what is the possibility here? So, option E is saying that by sending lipid raft inside the cell, cell membrane becomes more rigid in nature. By sending lipid raft inside the cell, cell membrane becomes more malleable in nature. C is by sending lipid raft outside the cell, cell membrane becomes more resistant in nature. And option D is mentioned here. By sending lipid raft outside the cell, cell membrane becomes more malleable in nature. So the option number B is correct here. And it's saying that by sending lipid raft inside the cell, and the cell membrane becomes more malleable in nature. Question number 6 has stated that calculate the Reynolds number for the microfluidic flow considering density rho is equal to 1000 kg per meter cube. Viscosity is around 0.002 ps. Velocity is around 10 micrometer per second. The diameter is equal to 10 microns. So now let's put this. The answer can be calculated using this formula. Reynolds numbers can be calculated using the uh, rho v v divided by mu. So we have rho is equal to around 1000 kg per meter cube, or I can write in the like this. Then we have v, so that is in micrometer per second. So we have to convert into the meter. So 10 to the power minus 5 meter second inverse second inverse, and also multiplied by d. D is also 10, so 10 to the power minus 5 meter divided by mu. Mu is equal to almost 0.002 uh, kg meter inverse second inverse. So second inverse will cancel out meter to meter cube cancel out. They cancel out. So whatever it is coming, we'll see. So it is around 10 to the power minus 5 times. So 10 to the power minus 7. So see this one. 10 to the power minus 7 divided by 2 into 10 to the power minus 3. So when as the, then if you consider this as a 1 into 10 to the power minus 8, then what will happen? This will cancel out with this one, 5, and it will be around 5 into 10 to the power minus 5. So this is our correct answer. And previous one, the correct answer was before also, the correct answer was A. So here we'll end today's session. Thank you so much for joining. If you have any doubts, please let me know. I hope you are able to hear me. So we have discussed all the things. Last time, also we'll discuss some more uh, uh, question answers. Thank you for joining. Please let me know if you have any doubts.